Okay, so let's start. I hope you had a good fall break, ready for the, I don't know, next 2/3 of the semester or something like that. So some reminders. You are working on homework too, I hope. Midterm, actually 2 more weeks. It's going to be in class or in another class if we manage to get a larger room, we'll see. We're going to give you a few examples of previous year's midterms. Basically, you have about an hour and 15 minutes, 4 or 5 questions, covering everything that we've done until then. So in the next 2 weeks, including the next 2 weeks, homework, quizzes, everything that you've seen. Just before that is the proposal's due date. So hopefully you are teaming up and thinking about it. The plan is for you to write a single page that explains what you're going to do. Hopefully this single page will already be written after you've investigated some and you know kind of what you want to do, you know what papers you want to look at, you want to, maybe you know what data sets you want to use if you are going to use any data sets. After the proposals are due, I'm going to schedule meetings with all the teams to talk about it. So it's going to take some time because there are many teams. But that's the plan while you are working on it. So, okay, I also want to remind you that unfortunately we got the last day of the exams period as our exam. Nothing that I can do. So just it only means that you are all staying here until the last day. It's December 19th. Questions? Okay, yeah. As I said, we'll give you examples. There'll be some multiple choices. There'll be some things that you have to write. Even for the multiple choices, you'll have to do some work in order to get to the multiple choices. So my goal is that it will not be determined by stupid mistakes. If you say that 2 + 2 is 5, that will not determine if you lose points or not. So we're trying to do it so that you know it forces you both to know what we've done. So if you just know what we've done, you should be able to easily get 60% of the questions. If you understand what you've done, you should easily get 80%, and if you can think a little bit about it, you should get 100. That's the goal. I don't know if we're going to succeed doing it, but that's how we're trying to design it. Other questions? Okay, so let's move on. Oh, okay, so one reminder, projects. You've already seen this slide. Go to the webpage, there's some suggestions there, and also a skeleton for the LaTeX file, or style file for the LaTeX file that you can use. Okay, so we are actually moving to another topic today, something that will force you actually, there's going to be some subtle things, so you have to be on your toes here. Here's what we're talking about. We're talking about transforming a feature space. Right? So we've seen this picture. We said, well, we cannot deal with it with linear models, so we're going to change the feature space. And now we can. And last time we've seen this example, again, the same story. We want to be able to separate the green from the blue. We cannot do it with a linear function. But if we change the feature space and we transform the original space of x1, x2 to a new space, which is x1 squared, x2 squared, now a linear function on top of this can work. And this is going to lead us to talking about the dual representation and the idea of kernels and the kernel trick, which we're going to spend time on today. So why do we even need it? So if we are transforming the feature space, basically it results in a much, much higher dimensional space. You've already seen this in the homework. You move from, in the slide here, from a k-dimensional space to an n-dimensional space. You know, think about what you've done with the badges when you invented features, where you, instead of, say, just characters, you move to conjunctions of characters. Or if you have words, in the context-sensitive spelling example that we discussed a few times, if you have 50,000 words and you represent things in the word space, you'll have order of 50,000 features. If you now consider conjunctions of words, then the number of conjunctions of size 2 of words is going to be order of 50,000 squared, much, much larger. So the dimensionality is larger, and now it allows you to learn linear functions. But of course, because the dimensionality of larger, everything becomes less efficient, and this is where kernels are going to come in. So we will show that even though you are working in a high dimensional space, you can compute as if you are in the original space before you blew up the space. So this is what we've done. We've ended last time. We thought again about Perceptron, and we've given this example. 4 examples. A positive one, x2 is also positive, x3 is negative, x4 is negative, and we've made mistakes on x1, x2, and x4. And we asked ourselves, what is the resulting W? After I started, say, with a 0 weight vector, and I have this learning experience. So what is the resulting W? Everyone should easily know this. Over there, someone wants to say something. What is the resulting W? No one wants to speak to me? Yes.
W plus W1, W2 plus W2 minus W4.
So W1
Plus W2 minus W4.
right, and the reason is that we add, sorry, it should have been x1 plus x2 minus x4. Okay? The reason is that we added x1 when we made a mistake on x1. We added x2 when we made a mistake on x2. We did not make a mistake on x3, so we don't care about it. We made a mistake on x4, so we subtract it. Everyone agrees? No questions here? That's really important here. We have to understand this. So basically, W's and X live in the same space. W is really a linear sum of the X's, okay, of the examples. So, and more generally, I can write the W this way. R times alpha I times the yi times the vector, the example, X superscript I, where R is just the learning rate. Let's think about it as 1 here. Alpha is the number of mistakes I've made, because if I've shown you x1 again and I made a mistake on it again, I will add it again. Y is the label, because I'm adding an example. If yi was positive, I'm subtracting it if it was negative, times the dot product. Okay, so that's W. So basically what we've done here is we've shown the W is just a linear sum of examples I've seen before, not all the examples, only those examples on which I've made a mistake. right? So these are the important examples. If I got it, I can forget it. If I did not get this example, I need to remember it because it's part of my representation of W. Now, really, I don't care about W. What I care about is how to make a prediction on a new example X. Right? So I care about, you give me a new blue X here, I want to compute f of X. And we compute f of X as a dot product W transpose X. And now I'm going to substitute for W what we've done here, and this is what I've done. So I've substituted W, transpose dot product with X here. And basically, so this is a number. R is a number, alpha I is a number, yi is a number. So this is basically a weighted average of these xi's. Everything here, all this linear sum, dot product with x. So I can basically open the parentheses and just put x inside, which gives me xi dot product with x. And the constants, the scalars are outside. Everyone agrees with that? I basically opened the parentheses. So what did I get? What I got is the prediction on the blue x as a function of the dot product of this x that I care about with all the examples that I've seen before. In fact, not all the examples, only those examples on which I've made a mistake. Because for those that I did not make a mistake on, this alpha I is going to be 0. Okay? That's the dual representation. So now we have a dual representation of the prediction. We don't care about W's. Everything is in the X space, if you want. Everything is a function of the example that I've seen before. So give me a new example. I'm going to compute my prediction relative to it as a function of the examples that I've seen before, which basically means don't maintain your W anymore, the way you are doing now when you're doing your homework too. Forget the W. Instead of maintaining the W, keep track of all the examples you've seen before on which you've made mistakes. Remember which mistakes you've made on each one. Okay? That's the dual representation. What does it give us? It will allow us to use kernels, and that's what we're going to start doing today. So it will allow us to actually be efficient in computing it. So really kernel-based methods is a method to run Perceptron or other linear algorithms, not all, but many others, on a very large feature space without actually incurring the cost of carrying without a large weight vector. And computing the dot product, which, if the dimensionality is high, also is going to take time. Now notice, and this can sometimes be confusing, it's going to be more efficient, but it's really only efficiency that it gives us, right? So the classifier that we're going to compute in the dual representation with the kernel trick, which we're going to introduce shortly, is going to be the same classifier, just algebra, exactly the same classifier as the one that we would have computed otherwise, only it's going to be evaluated more efficiently. So all the generalization, if one classifier, for some reason, we manage to show generalize as well, the second one is also going to generalize as well. The other thing, again, relative to the literature, sometimes the literature is a little bit misleading here, so I want to make sure we understand this. Kernels were popularized by support vector machines. That is a very good linear learning algorithm. You're actually playing with it already in homework 2, even though we'll introduce it just in about a week or two. But other learning algorithms can enjoy kernels, and I'm introducing it in the context of Perceptron because I think it's simpler and good to know. Another thing that you'll sometimes see in the literature, you'll see people said, we used SVM or Perceptron with linear kernels. What does that mean? It means they did not use kernels. Linear kernels mean we didn't use kernel, but it sounds much nicer, linear kernels, than no kernels. Okay, Basically, it means that they blew up the feature space explicitly rather than using kernels. Okay, so what are we talking about? So we want to deal with this function here. F of x is the sign of the dot product. I'm going to write it in a slightly different way here, just so we'll start getting used to it. So instead of writing it as the dot product, I can write it as the linear sum, wi xi. I can also write xi of x. Think about xi. Xi is the ith feature of x. So you can think about it as a function of x. x1 of x is the first coordinate, x2 of x is the second coordinate, and so on. It's really a function of x. Right? This is a good notation that we're going to use later. So now I want to transform this feature space to an expressive one. I'm going to choose for the running example that we're going to play with for the next few minutes, the set of all conjunctions over the feature space x1, xn, also called the space of all monomials over x1 to xn. So now, sorry. So now we're going to write a linear function as the sign of I is my index now. Instead of xi of x, it's ti of x, where t is a monomial. So now I'm running over all the monomials. If you think about it, there are 3 to the n different monomials over n features. So this I here is running over 3 to the n things. Ti of x, exactly the same thing. So it's the monomial evaluated on the point x. So let's just take an example of what I mean. If the monomial is x1, x2, x4, which means x1 and x2 and x4, it's a conjunction of this example. What I mean is it's 1 if x1 and x2 and x4 are 1. In this case, this works. x3 and x4 of the same example is 0. And x1, x2, oh, that's a mistake. I mean, of another example is also 1. Okay, so basically, I'm just writing it as a function of the example x. Everyone is okay with it? Yes?
So Ti is like one of those?
Ti is a conjunction. This is an example of a Ti. This is an example of Ti. This is an example of Ti. Right? And you just have to realize that the sum here is over 3 to the n Ti's like this. Okay? Every monomial over n variables. So there's going to be x1 there. There's going to be not x1. There's going to be x1 and x2. x1 and not x2. x1 and x2 and x3. x1 and not x2 and x3, and so on. Yeah.
Why is there 3 to the n?
Okay, why is there 3 to the n? So I have n xi's. What is the monomial?
Each one could be positive, negative, or neutral.
Right, so I'm going to write a monomial. I have n slots, and in the ith place, I can either put xi as a positive, put it as a negative, or not put it there. For example, here, let's assume that I have 5, n is 5. I chose not to include x1, not to include x2, and include x3 positively, x4 positively, not to include x5. Okay? So there are going to be 3 to the n overall. And that's my notation, right? So basically, all I've done here is two things. One, I moved from the x1 to xn space to the t1 to t3 to the n space. And I've written the function this way. The only thing for you to realize is that now this dot product here is in this space, which means I have 3 to the n different weights. So my sum now is over 3 to the n numbers. Okay? Yeah.
Why are these equivalent? Like, why are we using these?
I just chose this as an example. So I want to transform the feature space. Transforming the feature space meaning choosing a new feature representation. And I chose the conjunctions, the set of all conjunctions, as my new feature representation. You can choose only conjunction of size 3 if you want, or you can choose some other things as a way to transform the feature space. For example, here, here I chose conjunction of size 2, right? Degree 2 of the xi's. In the example that we are running with, and we're going to go back to this example later. In the example that we're running with, I'm choosing an even larger feature space, conjunctions of any size. Just an example, but it's a good example, as you will see, because it's going to be easier for us to see what is the kernel tree. Yes?
So if we look at that first example, like what is T literally? Is that resulting 1? Like what are you multiplying from these by?
Here?
Yeah, if you look at, let's just take like first example on the right.
So I have, this is, n is 5 here.
Yeah.
Okay? So I have 3 to the 5 different TIs, and I'm summing over these 3 to the 5 things. I don't know exactly what is the order, you choose your order. Let's assume the T1 is X1, T2 is X2, T3 is X, T5 is X5, T6 is not X1, T7 is not X2, and so on. So that's what I'm summing on, right? So for the you gave me an X, right? This X that you want to compute the function on, and I'm summing over 3 to the 5 elements where T17 of X, let's assume this is T17, T17 of X, if this is my X, is 1. So it's Wi times 1.
So it's the result.
Yeah, so basically this is a feature. It's a Boolean feature. Just like when we had before, it's actually here. What is xi of x? Is the feature. So it's a Boolean feature, it's either 0 or 1. For the same price, ti of x is also 0 or 1. It's the value of ti on the example x that you gave me. Okay? A set of Boolean features. So you can think about this in two ways. Either it's just a linear sum, wi times 0 or 1 here, or you can think about it as a dot product, the w, but now the w is of dimensionality capital I here, 3 to the n, and this is a vector of all the ti's evaluated at the point x. Okay? We're going to see more examples, but I want to make sure that you are with me here. Yeah.
You need to say that before we were just doing wi xi. Now instead of just plugging in x, we plug it in and compute ti of x and then multiply w with ti of x.
Yes. So here at the top, I just have x with the original representation, right, over the 0, 1 axis. Now I transform the feature space, and every example x is now represented as 3 to the n dimensional vector, where in the kth place is the value of the tk monomial on x. Okay? Yeah.
So before, when you're doing the initial sum, wi times xi, both
At the
w
top.
and- yeah, both w and x have n different values, right? They're length n.
So this is an n-dimensional vector here.
Yeah.
Sum 1 to n, right? So it's an n-dimensional vector.
But then once you go down, will w still be n dimensional?
No, it's actually a different w. We call it w, but really it's a different w. Now it's 3 to the n dimension.
The w also.
Yeah. Has to be. If I want to sum over more things, I have to have more w's. Okay? So, you know, let's just make this w a blue w. So it will clarify that it's a different w now. Okay, so we transform the space We still have a W, but it's a different W. Now we have a lot more coordinates to the W. Other questions? Okay, so, and again, this is how you want to understand. Essentially, I took an example and I transformed it from the 5-dimensional space to the 3 to the 5-dimensional space. And I'm giving here some example of what that means. You know, I'm going to make one more change that maybe will 110110. Okay, so I had a typo here. The example that I care about now is x is 11010. And what you see here is the value of x in 3 of the coordinates, out of the 3 to the 5. I don't have room to write all the 3 to the 5, but this is one of the coordinate, the x1, x2, x4 coordinate. This is the x3, x4 coordinate. This is the x1, x2 coordinate. Out of 3 to the 5 coordinates that I have. Okay? But again, it's a Boolean vector, only it's much, much higher dimensionality. So it's a very expressive function. In fact, any Boolean function I can express this way because it's essentially a linear function over conjunctions. Okay, so that's the representation we play with. It's going to stay with us at the top for the next few slides. And now I'm coming back to this N here, but that's the representation we have. We are working in a high-dimensional space. This is the update that we standardly have. We take W, we add X to it. Given that now we are working in a high-dimensional space, this is going to take time to compute. But of course, we got a lot of increase in expressivity. We can run Perceptron or Winnow, but of course, it's going, as I said, it's going to take more time, and convergence is going to take more time because it's going to be it's a function of dimensionality. Okay. Now, when I give you an x, the original x, and you transform it to this T space, exponentially many features in the T space are going to be on this example, which means updating this W equals W plus or minus X is going to take a long time. So this is really the picture that we have here, right? So we've seen this before. You know that you have an expressive function. You think that you may want to represent it in the X space, but it's too difficult to express, so you map it to a new space. In this case, I show it as, the space of this conjunction or this conjunction of these conjunctions. In general, it's going to be a linear sum of these conjunctions. Okay, so let's start to work in this feature space. So how does the W really look? My goal now is to start with the standard update, only realizing that I'm working in this T space, and using some algebra to go back to the X space, to the original space that we had. So consider the value of W in the prediction. I've already made some mistakes. Let's see what is the current W. Every mistake on an example Z make an additive contribution of plus or minus 1 to some of the coordinates. In the current example, everything is Boolean, right? So if the coordinate is 0, I don't care about it because I'm not going to change the W. If the coordinate is 1, I'm going to change the W. How will I change the W? I will either add 1 to the W, if the example is positive, or subtract 1 from the W. Okay? That's another reason why I like this to work in this space of monomial because everything is Boolean now. So it's easier for us to see how the W changes. Okay, so again, every example makes an additive contribution of plus or minus 1 to some of the coordinates of W. So really the value of W is determined by the number and type of mistakes I'm making on the examples I've seen. Let's write this explicitly. So I'm going to denote by P the number of examples on which I promoted. P stands here for promoted, could have stand also for something else. What example I'm promoting on? Positive example. So P could have said, I could have said set of examples on which we made a mistake and were positive. D is the set of examples on which we demoted, which means I made a mistake on them and they were negative examples. And M is going to be the union of these, which means M is the set of all examples on which I've made mistakes so far. Okay? Now I'm claiming that the function at a point x, which is this linear sum, I can write this way. So let's leave the sum over I outside. Inside, I'm putting the W. What is the W? Is the sum over P, those I promoted on, of 1. So how many ones will I accumulate? I will accumulate sum over Z is in P, and also Ti of Z is 1. If Ti of Z is 0, I'm adding 0 to the sum, right? I don't change the weight there. Minus the sum over the example I demoted, again, when Ti of Z is 1. If Ti of Z is 0, I'm not subtracting anything. Okay, so you should agree that this is the value of Wi. So this is, think about this, this is the 17th coordinate of W. I'm looking at all the examples that I've seen so far. I'm looking at their 17th coordinate. And I want to see how many times did I add 1 or subtract 1 to this 17th coordinate. Okay, that's what's written here. Everyone agrees? And of course, I'm summing it over all coordinates. So, but think about it as a single coordinate, number 17. And of course, this is times Ti of x, T17 of x. Okay? T17 was x3 and x4 and x5. Now I'm inventing a new notation, still sum over I. I'm going to call Ti of x is still here, and I'm going to replace everything that is here in these brackets with what I call Ti of z times S of z. What is that? This is going to stand for the sign, whether it's 1 or minus 1. And clearly, if Ti of z is 0, I contribute nothing to the sum. If Ti of z is 1, I contribute either 1, if it's in P, or minus 1, if it's in D, and this is where S of z is going to come in. It's going to be plus or minus 1. Okay, so saying it again, I'm highlighting here the x that we care about today. It's the blue x. This is the way we think about it all the time. It's just dot product, or the linear sum over all my 3 to the 5 or 3 to the n i's. This is how we wrote it before, and this is my shortcut notation where S of z is plus or minus 1, 1 if it's in P, promoted, minus 1 if it's in D, demoted. And I put here Ti of z, which basically means if you did not make a mistake on this example, it's 0. Doesn't count to the sum. Everyone agrees with this? Yeah.
How do we know the set of examples on which we promoted?
We just remembered it. As we go, we are now looking at the 100th example, and we remember we wrote all the examples from the beginning on which we made mistakes. Okay, so that's actually a very important question. So when we get to implementation, before, when you got to the 100th example, what did you have to do? You had to look at your W, your vector, that you maintain over the last 100 rounds, and compute the linear sum with it, the dot product. Now, I'm forgetting W. Instead of W, I remember all the examples that I've seen. Okay? And when you give me the 100x, this blue one here, I look at all the examples, each one of them. I threw out all those that I didn't make a mistake on. I kept only those I made a mistake on, and I'm computing this. Okay? I can do it if I remember the examples on which I've made mistakes. Everyone agrees? Okay, so now I can just write it this way. I basically put the sum of the, so what did I do from here to here? I basically reordered these two sums. I put the sum over the I inside. This is just a number, it's plus or minus 1, so I can just put the sum here. That's what I have. And this should remind you something. What is this? What is this part here? Sum over all the indices, Ti of z, Ti of x. What is the sum over all indices? It's a dot product. It's the dot product between the Ti representation of the z and the Ti representation of the x. Okay? What is a dot product? You take the first coordinate from here times the first coordinate from this, second from here, and so on, up to 3 to the n from the Ti of z and the 3 to the n Ti of x. So basically what I have here is a dot product of the x I care about. I want to make a prediction on it with a z, where the z is one of those examples on which I've made mistakes before. It's z in M. And so I'm taking all this dot product and I have a linear sum of them with plus or minus 1 coefficient. So plus if I made a mistake on it and it was negative, a positive, minus if I made a mistake on it and it was negative. Okay, so basically all I've done so far is just algebra. I started with f of x here, computed as the standard dot product between the w and the features. These are my features now, the Ti of x. And I forgot the w's and replaced it by z's, where z range on all the examples I've made mistakes on. Okay? Basically algebra. Okay, so again, I'm just saying what I've said before. A mistake on z contributed a value of plus or minus 1 to the w. I wrote it this way, and I basically got it as a function of a dot product in the feature, in the t space, and I'm denoting this dot product between x and z as the kernel of x and z. Definition. Okay? So now we got this standard notation. The prediction or the function value at x is basically sum over all the examples on which I've made mistakes, s of z, kernel of xz. Yeah?
Sorry, I still don't understand why S of z, Ti of z is equivalent to the previous statement on the previous slide.
Okay, let's see. Which step? From here?
So from there to the bottom next to the one.
Okay, so let's, this is a sum over all indices, okay? So let's just think about I equals 17. So what is the W17, the 17th coordinate of W? It started with 0. For every z that I've seen and I made a mistake on, I've either added 1 or subtracted 1. If z was in P, I added 1. If z was in D, I subtracted 1. So this is now the value of W17. You agree with that? So what I have here is W17 times T17 of x. The 17th coordinate of the T representation of my example x. And that is f of x. Now, I'm taking this W17, and I'm writing it this way, as the sum of all the examples, Tiz times S of z. Why is this the right thing? So let's assume I only made mistakes on positive examples. Okay, so this guy, the right side here is going to be 0. It's only this. So what's going to be the value of this? It's the number of examples on which I made mistakes, for which Ti of z is 1, because if Ti of z was 0, I wouldn't add anything. And therefore, it's equivalent to Tiz times S of z, which is 1. We said only positive. And we're summing over all those examples on which we made mistakes. Okay? Now, more generally, you'll also subtract those on which S of z is 1, or S of z is minus 1, because they are negative examples. So basically, we replace W17 here with this part, the sum of all examples on which we made mistakes, S of z, Ti of z. And again, a little bit more algebra. We move this linear sum from outside here, replace the order with this, because this is just a number, so it doesn't matter. And now we get something that is really a dot product in the T-space. Okay, if you're not 100% sure about it, take a 5-dimensional vector and do this. Just write it down and you'll convince yourself. Okay, so we got to this notation, which I call the standard notation. What does it give us? So far, all I've done is algebra. Instead of working in the W space, the standard space, I moved to the dual space. I represent everything as a function of examples I've seen before. You can think about this also as the distance between x and z in the T-space. Dot product really is a distance function. You can think about it as a distance function. But really the important thing is that the way I've written it so far, it's completely equivalent to what I've done before, and I may not want to do this, because now I have a huge sum to compute. 3 to the n elements here. The key thing is that now that I've done this algebra, I can actually show that we can measure this k of xz without blowing up the feature space, without moving to the T-space actually. I can compute it directly by looking at x and z, the original n-dimensional one, rather than the 3 to the n dimension. And again, let's do this in the example that I started with. This is really the heart of the kernel tree. The fact that I can take this huge dot product that is written here and compute it very efficiently. So we are playing with this example of the space of all 3 to the n monomials. And the claim is that this dot product between x and z in the T space is just 2 to the same xz, where same xz is defined as the number of features that have the same value for both x and z. So before we show that this is true, what does that mean? It means that I took a dot product that requires 3 to the n products, and I'm computing it by looking at the original n-dimensional space vectors, x and z. I'm just looking at them, figuring out how many of the bits are the same. This is going to take me n steps. And I'm computing 2 to this power. A lot more efficient, right? Everyone agrees that this is a good claim to have? Okay, so why is that true? Anyone wants to try to give a proof? Okay, so let's go over a proof and an example. So Okay, basically this is us rewriting this thing, and the cool thing is that now I've written f of x again in the original space. So I really work in the t-dimensional space, in the 3 to the n dimensional space, but I'm computing in the original space. Okay, so as our example, let's take n equal 3. Let x, the point I care about, be 0, 0, 1. And let's z, now there are many z's, all the z's that I've made mistakes on before, but let's take now one of the z's, and it's going to be 0, 1, 1. So let's think about what would happen when I compute the dot product t of x times t of z, which is this, right? Really, who's going to survive here, right? So in this linear sum. The only thing that will survive there is when ti of z and ti of x are 1. Otherwise, it's not going to contribute to the sum anything, right? Again, it's a dot product between vectors. Both vectors are Boolean, so it's written this way. And something is going to be added to this sum if and only if both ti of z and ti of x are 1. Okay? So let's assume that my ti is x2. That's my monomial. What is x2 of x? 0. So it's not going to contribute. I already know. I don't need even to think about x2 of z. Let's take x3. What about x3? 1. x3 of x is 1. x3 of z, also 1. So the monomial x3 is going to contribute. What about not x2? Not x2 of x is 1. Not x2 of x. Not x2 of z, 0. Yes?
So I'm not sure this is correct. So for example, if x and z both were single dimensional, so x is 0, z is 0. In that case, I think the value of this would be 1, because only the literal,
Right.
both of them are not present as 1.
Right. So we also have, because we have 3 to the n monomials, we also have an empty monomial,
Yeah.
right, where nothing is included.
Yeah,
So
that will be the only one which will be.
that would be the only one, and this is where the 1 is coming from. So let's deal with this. So we have, again, because there are 3 to the n, there's also an empty one. But let's think about all of them. The empty one is a kind of really a side case. So give me a monomial of size 2. Let's try to take a monomial of size 2. For example, let's take x1 and x2. x1 and x2 for x is, of x is?
0.
Not good. So let's take something else. So give me a suggestion for a monomial of size 2 that you like. Yes.
Not x1
And x2, not x1 and x2.
Not x1 and x2. Okay, let's try not x1 and x2.
X is 1.
Not x1 and x2 of x is 0. Not good. Another one. You had a suggestion?
not x1 and x3.
Not x1 and x3. Let's try not x1 and x3. What happens to not x1 and x3 of x?
1.
What happens to not x1 and x3 of z? So this is a surviving monomial, right? In the dot product, let's assume this one was for I equals 17. This is going to survive and add 1 to the sign. Not x1 and x3. If you know that not x1 and x3 does it, immediately you know something else that does it. if not x1 and x3 survives, yes?
Then either of the two, not X.
Either of the two, right? So not x1 must also survive. Because if not x1 and x3 evaluates to 1, it's a conjunction. Each component of it also evaluates to 1. So not x1 survives, x3 survives. Do you agree? Not x1 of x and not x1 of z are both 1. x3 of x and x3 of z are both 1. And the empty monomial always survives. It's always 1. So basically what we've shown, and I'm going to jump directly to my example here, red is not here because it's easier to write. Can you see this at the top? So this is the example that you led me to, not x1 and x3 of 0, 0, 1 is equal to not x1, x3 of 0, 1, 1, it so happens. Both of them are 1, and they survive. Because they survive, each subset of them also survives. So not x1 survives, x3 survives. And in general, if you find the largest monomial that survives, all its subsets survive, and that's it. Nothing else will survive. Only the largest one and all its subsets. Yes?
From a computational perspective, isn't it easier to find all of the subsets and add them up into a big number?
Yeah, I'm not computing it now. I want to understand what's going to survive. So the largest monomial that satisfies both is going to survive. How many elements are in this largest monomial that survives x1, x and z? Same of xz, right? I defined it by looking at which features are the same between x and z. So what are the features? x1, not x1 is the same, right? Both of them are 0. With x2, there's nothing I can do here because they're different. And x3 is the same, so it's not x1 and x3. So basically, I define the monomial of size same x and z, and I take all the subsets of it, including the empty subset. So the number of the monomials that survive is 2 to same xz, because given a set of m elements, the number of subsets of this set is 2 to m. That's something that you know. Yes?
So that sounded pretty crucial. Could you do that one more time?
Okay, so if I have a set of m elements, how many subsets do I have for the m elements? 2 to the m. Why? Anyone can give me a reason of why the number of subsets? So think about, I have a set of m elements. Let's call them 1 up to m here. I want to consider the subset. You wanted to give me a reason?
You either include
Well, exactly. So think about this set, 1, 2, 3, 4, up to m. I want to choose a subset. How do I choose a subset? I'm going to take a vector of size m. The first element corresponds to the first element in the set, the second corresponds to the second element, the mth corresponds to the m. And when I say that it's 1, I mean include it in the subset. When I say that it's 0, do not include it in the subset. So I define every subset as a 0, 1 vector over these m elements. Okay? So basically, I have m options, and in each case, I can include it in the subset or not include it in the subsets. So it's 2 to the m subsets. Okay? So what I showed is that I proved this claim. Right? I proved that I can compute this big dot product with 3 to the n, dimensions by looking only at n dimensions, just looking at the original vectors, and that's it. Everyone is convinced by that? Now this is just an example. So we took one transformation, we started with x, the x space, and we transformed it to a very, very big space. We said, this is good, it's going to add us expressivity, but it's going to cost us, because now the dot product is going to be in a huge dimensional space. So the next step was to show this trick and show, no, it's not going to cost us. We can actually compute this dot product efficiently. Now remember, this is just one example, right? So every time you want to transform the feature space, just like I did here, you'll have to do the same thing, right? So you'll have to transform it and then figure out, can I compute it efficiently? The good thing is that actually there's going to be a theory that will say, yes, you can, under some condition, you can always compute it efficiently, which we're going to get to in the next few minutes, just to make sure that we get this. Yes?
If the features were not Boolean and real value numbers, this would not work.
Yeah. We're going to get there. Yeah. So this is just simpler to understand, I think. We're going to do the same thing with real value features.
How do you know that this normal transformation is actually going to be a because more features doesn't necessarily mean this?
Well, it's clearly more expressive, right? So clearly there are more functions that I can express with these monomials than I could have expressed with the original features. That's for sure, right? So, in fact, with this specific transformation, I can express all Boolean functions, while in the original space, I could express only linear functions. Yes, no? No, it's true, right? So every Boolean function is, can be written as a DNF, for example, as disjunction over conjunctions. This is a linear function over conjunction, which is as good as a DNF. So I can write any Boolean function this way. So I added expressivity. As we know from the beginning of the semester, adding expressivity is not always the best thing because I can overfit. But at least if you give me a set of examples that were not linearly separable, now I'll be able to express them. I'll be able to learn a function that fits them exactly.
Is there any case that there's going to be a linear separation?
Yes. In the space of all Boolean functions, every function is going to be linearly separable in the space of monomials. Because every function can be written as a linear function over conjunctions. So, but even if this wasn't true, if I expanded not to the set of all monomials, but only to the set of monomials of size 5, right? Conjunction of size 5, even though my space is of 100, dimensionality 100, even then I know that I increase the expressivity. I don't know if it's sufficient, I don't know if it's too much, but I know that I added expressivity because there are functions that were not linearly separable in the original space and now become linearly separable. That I know. So, but again, at this point we are just playing with how to do things, not necessarily with, is this the right thing to do? Or is this, how to choose which transformation to make is a very hard problem, and in fact there's no good theory for how to do it. It's really, in some sense, a trial and error. We're going to talk a little bit about it. But definitely, we are in the right direction in the sense that we want to add expressivity. Because we could not feed the data with the original representation. Right? Again, we'll think about the example of the ellipse that I showed before, right? So I wanted to split the green from the blue. I couldn't do it. So I want to increase expressivity. We were lucky, and increasing expressivity to dimensionality 2, degree 2 of the polynomial was good enough. So we're going to get there. But at this point, I want you just to understand this Here's another example for you that you can play with at home. Take this four-dimensional case. This is x, this is z. 3 to the n in this case is 81. So you can actually write down, if you want, 81 monomials. Before you finish writing the 81 monomial, I think you'll convince yourself how to compute the dot product in this space. I call it here I of x dot product with I of z. And I want you to show that for these two examples, x and z, the dot product of them in the T space is going to be equal to 8. So we have two ways of doing it. One way of doing it is write down 81 dimensions and figure out among these 81 dimensions which one are going to be 1 for both x and z. And another way of doing it is just to look at x and z, figure out how many of the bits are the same, and do 2 to this number. And you should convince yourself that that works, and really you get 8 in both cases. Okay, so what have we done? We developed the dual perceptron. Basically, we developed a new algorithm that says, simply run Perceptron in an online mode, but keep track of the set M, the set of examples on which you made mistakes. Once you know you have the set M, you also have the set S of Z, which is whether the example was positive or negative. So basically, rather than remembering W, remember M, which is P and D, and then use the dual representation in order to compute it. Okay, so let's take one other example. So what is the game we're playing here? We know that prediction with respect to a separating hyperplane W that our algorithm gave us, Perceptron or SVM, instead of doing this, we're going to compute the prediction as a function of the dot products of the feature-based representation of x with some of the examples we've seen in the past. Right? That's the game we're playing here. Right? So we replaced the prediction that is a function of W with the prediction as a function of the dot products with some of the examples we've seen in the past. Okay, that's the game. That's the dual representation. That's even before we transform. Now we want to do this in a high-dimensional space. So let's take the following example. I have two examples in the n-dimensional space, x and y. I want to map them to a high-dimensional space, and in my example here, it's going to be a quadratic space. So this is the transformation. I call the transformation phi. Phi of x is going to be now the following two-dimensional vector. The following vector with two-dimensional features. 1, x1 up to xn, so I maintain also the original features. x1 square, x2 square up to xn square, and then all the mixed products, x1 and x2 up to xn minus 1x. So this is my continuous example, right? So now I don't care what x1 and x2 are. They could be Boolean, they could be real value. So what did I do here? I started with an n-dimensional vector. I transformed it to what? But what is the dimension? What is the dimension of the new vector, of the phi? In this case?
3n plus.
Why?
3n plus 1.
So I have n here, right? I have n here. How many do I have here? N squared, really n choose 2, right? All the pairs. So really this part is the one that determines the size. Right? So it's order of n squared dimensionality. So I move from n to n squared. Could be a lot, right? So if n is 1,000, I move to 1,000,000. Okay? And the same thing for y. So I increase the dimensionality of the space. Now I want to compute the dot product there because the dual representation showed me what you want to do in order to make a prediction on a new example is to be able to compute dot products in this new space. Right? So I want to compute phi of x transpose times phi of y. That's going to take me time that is about n squared. Okay? Because that's the dimensionality. Instead, the kernel trick says you can actually compute it in the original space. How? Before we showed one way to do it in the discrete case with the same xz. Now I'll give you another way of doing it because the transformation is different. Here what I'm going to do is I'm going to take the original vectors, do the dot product of them, add 1, and square this result. Okay, remember, this is dot product is just a number. A is a number. B is also a number. It's dot product plus 1 all squared. And my claim is that A is equal to B. So I don't need to work in the n square space. I can work in the n space. Now, in fact, I'm cheating a little bit because the coefficients do not really matter. So really, I had to confuse you even more and add square root of 2 to these guys here, to the mixed terms. But it really doesn't matter. So you should be able to prove this to yourself, right? To take this, just compute it, right? So what will you get? You'll get x1 times x2, x1 times y1, x2 times y2, and so on. You'll get all the mixed terms in the first step, and then once you add one to them, and square it, you'll get all the other terms. So just do this exercise, and you'll see what happens. So this is really the kernel trick in another example. Okay, so now I can go the other direction. So here what I did is I started with original vectors. I wanted to, I transformed it to a high-dimensional space. And I showed you later that this is equivalent to a computation done in the original space. Really, we can do it in the other direction. So really, what is the goal? I want to work with degree 2 polynomials, for example, as in this example, phi of x. But I know that the dot product will be in a space of dimensionality n choose 2. I'm writing it's n plus 1 over 2. And the kernel trick allows us to save the computation and compute the dot product in the original n-dimensional space. Okay, so can you do it for every k? Just define a k and do it. It turns out that any function that corresponds to a dot product in some dimensional space becomes a kernel. So the kernel trick applies whenever your k corresponds to some dot product. So let's take another example. I'm going to give you another quadratic kernel. It's going to be a little bit different than the other one. So here, as I said, I'm starting with k. Now I defined k here directly in the original space. It's basically a dot product between x and z squared. It's a little bit different than before, because before I also added the 1. Here I don't add the 1. And I argue that this is a kernel. How do I prove to you that it's a kernel? I'm going to show you that it's actually a dot product in some space. You would expect that it's a dot product in some space of dimensionality n square or something like that. So I'm basically writing it this way. I'm taking the case of n equal to, so we can actually simplify things. So I'm defining k of xz. How did I define k of xz? It's x1 z1 plus x2 z2. Everyone agrees with that? That's just the dot product of x and z. square. So basically, I took this definition from here, and I wrote it here. This is my two-dimensional case. Now let's open the square here. So what I get is x1 square, z1 square, x2 square, z2 square, and this is the mixed term, 2 times x1, z1, x2, z2. And now I'm decomposing this as a dot product. I'm claiming that instead of writing it this way, I can write it as x1 square times square root of 2 x1, x2 times x2 square times the same thing with z. Okay? Everyone agrees that this is the same? Just follow the algebra. So basically, what did I do? I started with a definition of K. I didn't know whether it's a kernel or not. And I showed you that it's a kernel. How did I show it's a kernel? By showing that I can write this K as a dot product of two vectors in a three-dimensional space. So I blew up the feature space. Well, not really blew up because I just moved from 2 to 3 because we started with low dimension. But the idea was that instead of working, this is really the space I want to work with. Instead of working here, I can work directly here. And this is really this example that we started with, right? So instead of representing the blue and the green x's this way, I'm presenting them in this space, the quadratic space, and now I can make predictions there. I can learn a perceptron in this space. Questions? Yeah.
The previous slide for the K function, we also had a plus one, one plus something.
Yes.
Square. Where did this go?
So it's just a different function. Basically, there are many kernels. We already saw today 3 kernels. One in the discrete space, all monomials up to degree n. 2, the kernel 1 plus x times dot product y. 3, just the dot product squared. So these are 2 different kernels. In one case, I included the 1, so I got more terms. In the other case, I didn't include the 1. Yes?
So 2 questions actually. The first is, if you have a less trivial distribution, how do you know what kernel would be helpful?
Okay, so let's defer this to next time. What kernels do I want to use? So now we are just believing that kernels are useful, and we're trying to understand, what does it mean and how to compute it.
Okay, cool. And then the second one was in the first case, where we have the conjunctions, we were able to reduce it to 2 powers saying whatever. What can we reduce these to?
Yeah, to this. Instead of, okay, let's start with the previous example. Okay, so this is my blown up space. This space, which is here, size n square, is, I'm pointing to the phi of x1
Oh, gotcha, yeah.
and the phi of y, the phi of x and the phi of y. This is my blown up space. This is equivalent to the 3 to the n space that I had before. Now it's only n squared. Okay, still a blow up, but not such a big blow. And what I'm saying, instead of computing A, which is a dot product in an n square dimensional space, I'm computing it in an n dimensional space. Before, in the example, instead of computing in a 3 to the n space, I computed it in an n space. But in both cases, I want to work in a high dimensional space. Rather than computing the dot product in this high dimensional space, I'm computing it in the original space. Before it was 3 to the n, and we moved back to n. Here it's n squared, and we move back to n. And similarly, here, also n squared. The space that I'm really working in is this, 3 dimensions. But I don't need to touch 3 dimensions. I can work in 2 dimensions here, in the X transpose here. Okay, so again, the gain here is just 1 dimension because I started with n equal 2. Do the same exercise with n equal 5. The gain is going to be larger. So there's a lot of stuff that we did today. Really go over it to make sure that you understand, but the bottom line is here. I want to transform the space to a higher dimensional space, and I want to do it without incurring the cost of computing dot product in the higher dimensional space. That's the idea. Yeah.
These two kernels are not really as, like the difference between the dimensions is not as good, right? Because like for these kind of things, if we even have more than 500 examples, it's probably beneficial to use the W.
Okay, so good question. So the question is, when do you want to use this Kernel trick and when you don't? And it's true that sometimes, even though you can use the W, you don't want to. And we're going to talk about it next time. So, but again, at this point, I don't want to get to when, but rather to understanding what is the kernel trick. And we're going to talk about when it's beneficial next time. Okay, see you Wednesday then.
One question regarding the homework group. So, Adam had...
Okay, one second. So there's a question on the homework that I'm sure you care about.
Adam is not exactly a mistake learning algorithm. Because even if you don't make a mistake, but you don't complete it, okay.
Yeah. It's still online, but it's not mistake. Yeah. Say it again. Yes. X is the example that I care about now. I want to predict f of x. So I put it as a blue x. No, so X is my current example. Z is one of the previous examples. X and Z. No, Z is any of the examples on which I made mistakes. X is my current example. Yes, so notice that I'm doing a sum over the set M, which is the set of all those examples on which I made mistakes. And Z is a member of this set on which I made mistakes.
So, for example, I made a wrong prediction on 2, 1, 2, 3, and
Okay,
Xi
so
as the first, the fourth example, and then I need to calculate the x1 dot c1 plus x1.
Exactly.
Okay, thank you.
Yeah. Why?
I'm just looking for, because most of them have already formed groups and either 1 or 2 of them. Or would you recommend doing it just single or with 2 people?
No. I actually think that 1 or 2 is going to be difficult. 5 is also difficult. I think I said it in the Piazza. So, first of all, my experience has been that 5 people is a large group, and it's not easy to coordinate. And it so happened that, 1 person or 2 are doing the project, and the others are observing. 2, the expectation from a group of 5 are going to be about twice as the expectation from a group of 3 or 2.5, right? Because you have a lot more time. So I recommend not to do 5 unless they are really just impossible otherwise. 1 is definitely not a good thing. see, if you cannot find 2 or 3 or 4, I mean, we'll eventually accept things, but I just recommend not to do 5. I think it's too much.
At 1 or 2 would
2 is better than 1. 3 is much better than